All right, welcome to the video on coupled masses. So this section of the book has to do with two masses that are connected via a rope or string that passes over a pulley that will change the direction of that forces are applied. So this video will consist of two parts. First part, I'll go over the example in the book, and then the second part will go over this example problem that I have written. So the example problem is actually not as tough as the problem in the book. All right, so the problem in the book features a block on a ramp, which would normally just slide down the ramp. Right, there's no friction in this problem. So the block of mass capital M would slide down the ramp, except it's connected over a pulley. So it's connected by a string over a pulley to a mass lowercase m that's just hanging there. So the angle of this ramp is theta. The angle of the ramp's inclination relative to the horizontal is theta. Now, we don't know, just by looking at this picture that I've drawn, we don't know what direction the system is going to accelerate. We don't know if lowercase m is going to go down or up based on the given information. Now, if lowercase m is more mass, if lowercase m is a higher mass than capital M, then this will go down for sure, no matter what. If capital M is larger, it's a little less clear. It'll really depend on the angle theta. So you can imagine two extremes. If theta was 0, lowercase m would go down. But if theta was 90 degrees and the capital M was bigger, then the mass, this bigger mass would win out. You know, we would have the case where they're both connected like this, and the capital M would win and it would go down and lowercase m would go up. So actually, we don't know the direction of the system. We're going to have to leave that general. So the system's direction, so even though we don't know the direction it's going to accelerate, we do know that the rope will be taut throughout. So if capital M was going to go this way down the ramp, this mass is going to go up with the same speed at all times and the same acceleration at all times. Okay, so these two masses have the same acceleration, not the same direction of the acceleration, but the same magnitude of the acceleration and same magnitude of their speed, even though they don't have the same velocity. Okay, so I'm going to consider this to be like the positive direction. So a positive acceleration is one where this mass will go up and this mass will go down, down along the ramp, right, like that. Okay, so that's what I have in mind. Let me be a little bit more careful about directions now. So I'm going to define the I hat direction to be along the ramp, and the j hat direction to be perpendicular to the ramp. Okay. So let me draw a free body diagram for both of these two blocks. So we have mg, capital Mg, and we have the normal force from the ramp. Those are the only two on that one. And then for this one, and then the tension, T, is pulling back on capital M. So those are the three forces for capital M. For lowercase m, there's only two. There's only the same tension, and I'll explain later why the tensions are the same. The tension's going up, and then lowercase mg is pointing down. So two forces on the free body diagram for lowercase m, three forces for capital M. And for capital M, it actually, so as we did on the video for when we talked about blocks on ramps, it's nice to decompose gravity into the component along the ramp and the component perpendicular to the ramp. So if this is capital Mg, I just want to point out that the piece along the ramp is, capital Mg sine theta, and this piece is capital Mg cosine theta. So if that's not clear, you're going to want to pause the video and make sure that that makes sense, and maybe review the video on blocks on ramps. Okay, so if we look at some of the forces as Ma is equal to Ma for capital M. So first we're going to look at capital M. Some of the forces on capital M is equal to capital M times its acceleration vector. So we can look at the j and the I hats separately. So this equation is a vector equation. It has j components y components and x components. The y components aren't too there's not too much information contained there. So let's separate the y components and the x components of this equation. So all the y components are saying is that so the only force that has a positive y component is n, and all of the normal force is in the y component. Let me zoom out a little bit. Okay, so that's n, and then there's only one other force that has a y component, and that's the y component of gravity, which is actually in the negative j hat direction. So this is going to be a minus capital mg cosine theta is equal to may. And actually, because there's two blocks, let me actually call this am. So this would be the y component of am. But that's 0. We definitely know that capital M is not going to come off of the ramp. Okay, the n is just in response to the component of the weight that's going into the ramp. And the ramp, it has two options. It can either break, but assuming the ramp doesn't break, it's just going to push back on the mass enough to where it doesn't break. So we definitely know this thing isn't going to crash into the ramp, assuming it's strong enough. So this is equal to 0. So that stuff is equal to 0, and this just tells us the normal force is mg cosine theta. So that's true, but not really useful for analyzing for finding the acceleration of this problem. Right? It would be helpful if we had a frictional force as well, and we needed to find that frictional force. The frictional force would depend on this normal force. But because this problem doesn't have friction, actually, we're not going to need that part. The x component. So now there's the x component is interesting though. So there's the component of gravity that's along the I hat direction or x hat direction is mg sine theta, and that's the positive piece. That's the force that has a positive x component. And then the only other one that has a non-zero x component is the tension. The normal force has a 0 x component. So this we're not going to set equal to 0 because we don't know for a fact that the mass is not moving along that direction. So this is equal to capital M times acceleration of that mass in the x direction. Okay, now you'll notice that for your book, so on the left-hand side right here, your book never, so your book just says A. Right? So it's only at this moment that we say, well, this acceleration, the y component of the acceleration is 0. This thing, let's just call this A. A capital Mx, let's just call this A. So it's understood that if A, this thing that I just called A, if that's positive, then that means that M is going this way down the ramp. And remember, that also means, so A positive is also means that lowercase m is going up. Okay, so at this point we're defining, maybe I should even make a different color here. So we're going to define this to be A. So if A is positive, that thing's going down. Okay, so just rewriting our equation here, we have MA, and this is going to be the equation that your book has right here. Capital Mg sine theta minus T is equal to MA. So this is exactly what your book has right here. Capital Mg sine theta minus T equals MA. Okay, now lowercase m, if we look at F equals MA for that, so we're looking at sum of the forces on lowercase m is equal to lowercase m times that acceleration. Here there's only one really interesting direction, right? There's nothing going on in the horizontal direction here, only the vertical direction. So we're going to call this, so this is going to be the positive direction. Vertically upwards is the positive direction. And the reason for that is on the right-hand side, we're just going to write MA. So notice this is a vector equation, but this is going to be this is just the component along the interesting direction. This is the vertical component, taking the upward direction to be positive. Okay, so if we're going to set this equal to MA, positive is upward by definition. Remember, positive acceleration means lowercase m is going upward. And so we have to write this as t minus mg. Not mg minus t, but t minus mg. All right. And this is what allows us to, so it's the fact that this a is exactly the same that lets us use the same a in these two equations. Because really we would have an a subscript m and an a subscript capital M, but because they're coupled masses, that's the name of the section, we're allowed to do this. So then solving these equations is pretty easy. We can take equation 1, and this is a really common technique, by the way. We're going to add equation 1 and equation 2. So what that means is we're going to add the left-hand sides together and add the right-hand sides together. And the reason we're going to do this is that we have two equations for two unknowns. So our two unknowns are t, the tension, and a, the acceleration. Now what we care about, the point of the problem is to solve for the acceleration. Well, maybe it is, maybe it isn't, but we're going to try and reproduce this acceleration 4.32. So we could solve these two equations for these two unknowns. If we want to solve for the acceleration, notice how when we add equations 1 and 2, the tensions cancel out. We have a minus t right here and a positive t on this side. So when we add the two left-hand sides together, the minus t plus t cancels out. And we're just left with capital mg sine theta. So minus t plus t, 0, and then minus lowercase mg. And then we add the right-hand sides together. So this is capital M A plus lowercase m a. So we can factor out the a, and we get that right there. So then, if we're solving for a, we can just divide both sides by capital M plus lowercase m. This is mg sine theta minus lowercase mg over m plus m. And this is exactly what your book gets right here. Your book factors out a g. So it's a equals g, and then this thing in square brackets must be dimensionless, right? Acceleration, acceleration, so this thing had better not have any units. And we can make sure of that. So it's capital M sine theta minus lowercase m. So it's mass over mass. It looks like that's dimensionless. That's good. So you could see that there's a fight between these two things. It's the component of the capital M's weight along the ramp compared to lowercase m, compared to the mass that's hanging. So whichever one of those two things is going to determine which direction the system will accelerate. All right? So you can see also the dependence on theta right there. I said I would come back to why the two forces have the same tension. So even if the system is accelerating, even if this thing is moving, even if the pulley starts rotating right here, the two tensions are equal. So that's true as long as the pulley is massless. So these two tensions are equal because we have a massless pulley. Now we're going to come back to this. We're going to come back to this when we talk about rotational dynamics. And if the pulley has mass, actually to get it to rotate, these two tensions won't be equal. So if we imagine the system is accelerating so that it has positive acceleration, so the capital M mass is going down the ramp. If that were the case, then its tension, the tension connected to capital M, would have to be bigger than the other one in order to get the pulley to start moving. But we'll see in a few weeks that a massless pulley, there can't be any net torque on it. Otherwise, there would be an infinite rotational angular acceleration. So your book mentions this. It's kind of like, well, we'll come back to that point. But just know that if those tensions weren't the same, then and the pulley was near small mass, then we would get a logical inconsistency. But to understand why that is, we're going to need the rotational analog of Newton's second law. So we'll come back to this. So maybe wait until you see this equation. Sum of the torques is I alpha. So that looks a lot like sum of Newton's second law, right? Sum of the forces is ma. Sum of F equals ma. So this is the rotational version of Newton's second law. So basically, if the pulley is massless, this is 0. This thing I, whatever it is 0. So this has to be 0, the sum of the torques, which tells us the two tensions have to be equal. Okay, so this is kind of a subtle point, but just for now, just know that anytime you see massless pulley, you're allowed to assume that the tensions appearing on either side of the rope connected to that pulley are equal, even if the system is accelerating, even if the pulley starts rotating or is changing its rotational speed. Okay, we're ready to analyze this problem now. What is the acceleration of the system when released from rest? All right, so let's go back to that original problem. Let's do orange. Haven't done orange in a while. Original problem. So which one was capital M? Or M1 and M2. M1 is on the table. Okay, so we have M1. There's a tension. And because there's only one rope in this problem, I'm just calling it T. There's M1G, and then there's the normal force. And there's only one normal force in this problem, so I'm just going to call it N. If there were more than one normal forces, I would probably give it a subscript 1, because it's the one connected to M1. And then for M2, that's the thing just hanging there. There's a tension, and there's M2G. Okay. So each of these has a Newton's second law associated with it, but I just want to point out that I want to choose, I just want to deal with one acceleration. There's one acceleration in the system. So I need to choose which direction is positive, is my positive acceleration. Now, if there's no friction, there's nothing acting on this mass, M1, to the left. So I definitely know that this thing is going to go to the right, that M1 is going to move to the right, which tells me M2 is definitely going to move downward. Okay, so I automatically know, just from this problem setup, that the tension is less than M2G. Looking at this and knowing that it needs to accelerate downwards, that means that downward force needs to be bigger than the upward force. So I definitely know my system is going to, I know the system is going to accelerate in such a way that M2 is going to go down. So I'm going to call this is the positive acceleration direction. So when the system moves like this, that's going to be positive acceleration. So this tells me what direction to call my plus x direction. So I'm going to do F equals ma, and I'm only going to focus on the component that's non-zero, the component of the acceleration that's non-zero. So the one on the left, M1, there's only one force in the horizontal direction, so let me just write some of the forces on M1 is equal to M1A, 1. So that's true for the vertical components and the horizontal components. The vertical components just are equal and opposite. N is equal to M1G. That's fine, but that doesn't really help us in this problem. So I'm going to focus instead on the T equals M1A. Right, A positive. So T is the magnitude of the tension. The left-hand side is positive. The right-hand side needs to be positive. So A is positive. So this equation is kind of defining what we mean by A. So we're introducing A, so we have to be consistent when we use it here. So in other words, I'm going to do, so this definitely equals F equals ma. This is definitely true. But if I'm going to set the right-hand side of this one equal to M2A, this definitely means that this is my positive direction. Okay, so I have to write this in the order M2G minus T. See how so we're saying the right-hand side is positive, so I have to write it in this order. M2G is definitely bigger than capital T. So then we solve by elimination. We add the left-hand sides together, where the T's cancel out, so we get M2G. And then the right-hand sides, when we add them together, it's M1 plus M2A. So the acceleration of the system is M2 over M1 plus M2 times G. Right, and that's our answer. So how quickly the system accelerates depends on how big M2 is compared to the total mass. So if all the masses are the same, then the fact that they're connected will decrease the acceleration due to gravity by a factor 2. Right? If m2 is close to 0 mass, you could see that it's hardly pulling on the big mass at all, and so the acceleration goes to 0. If m1 goes to 0, then the acceleration is basically gravity. So that's like, so in the picture, if m1 is just like a speck of dust, it's not going to really hold back on m2 at all. So m2 will just undergo free fall. So it makes sense in those limiting cases, which is great. If we needed to solve for the tension, you would just take acceleration, plug it back into either one of these two formulas and solve for t. So plugging it into the left-hand side would probably be the easiest case. And you can get the acceleration that way. Great.